I thought I would take a few minutes here and step through each of the three homework problems that we had for the first week of class. So what I've done is I've already queued up the data sets for those using the Import Dataset button over here in R. So you won't see me go through this sort of import dataset wizard here, but I've already got the data sets that we need for music festivals, for Chipotle burritos, for Mercedes S-Class, and for Austin Food Critics. So let's just start right away on problem 1A, where we were looking at data on music festivals, major music festivals in the United States. So if we take a look at the first 6 lines of that data set, you can see every row corresponds to a band, and we've got a dummy variable, yes or no, did this band appear at each of these 6 major music festivals, Austin City Limits, Bonnaroo, Coachella, Lollapalooza, and Outside Lands. We've also got a variable saying which year, and this data runs 4 years, 2008 to 2011. So, first things first, let's just make a table to compare how correlated attendance at ACL was with some specific other festival. Let's take a look at Bonnaroo. And this table right here, I store the result in table 1 and output the table to the screen by asking for table 1 right there. And it looks as though there might be an association here, that the bands who played at Bonnaroo maybe had a slightly more likely chance of playing at ACL than those that didn't. That's a little bit hard to judge using a table of raw counts. And so one of the things we learned to do on the Titanic data set in class was to turn this table of counts into a table of proportions. So what we'll do is we'll call the function prop.table using this table 1 as an input, and we will also ask it to normalize by column, and we do that by saying margin equals 2 as an optional flag to the function. So there we go, and you notice that each of the proportions in each of these columns here sums to 1. And so it looks like among those bands that did play at Bonnaroo, this variable is equal to 1. 18% of them went on to play at ACL, whereas among those that did not play at Bonnaroo, 0 over here, about 11% went on to play at ACL. So that's clearly a lift, and we could quantify that using relative risk. And this can get a little tedious depending on how much copy and pasting you did to make these commands. What you see here on lines 11 through 12, I've just chained those 2 sets of commands together, where we make a table of counts using the xtabs function, and then we feed that into the prop.table function for each of these 4 festivals right here. So Bonnaroo, Coachella, Lollapalooza, and Outside Lands. And if you kind of scroll back through the results right here and you start comparing, it looks as though it's probably either Bonnaroo, 18 versus 11, or Lollapalooza, about 17.5 versus 10, that is most strongly predictive of attendance at ACL Fest. And if you're very careful, you go through, let's just take Lollapalooza as an example. Let's take that table of proportions and call it lol table for Lollapalooza. Now this is the raw input if we wanted to compute relative risk. So let's take this cell of the table divided by that cell of the table. That would be our relative risk for appearing at ACL among those bands that also appeared at Lollapalooza. So that's the second row, second column, divided by the second row, first column right here. And it appears that our relative risk for Lollapalooza here was 1.73. And if you go through carefully and calculate that for all of the other festivals, it seems to me at least as the Lollapalooza is the most strongly predictive. Okay, so it seems there's something to those theories that that music festival fans have, that attendance at one festival, certain festivals at least, predicts attendance at Austin City Limits. Okay, let's take a look at 1B, which is the second warm-up problem, looking at calorie counts for burritos ordered through Grubhub at Chipotle. Okay, so each meal here is represented with only a single variable, which is calorie count. If we ask for a histogram, there's a lot of individual data points in this data set, hundreds in each bin here. And so it's very natural, given the size of this data set, to think about discretizing it into finer bins. So one of the things I ask you to do, this looks like the bins are maybe 200 in width or something. Instead of bins that are 200 calories wide, let's make bins that are 40 calories wide instead. So the way I'll do that, we know that the data runs from 50 at a minimum to 2570 at a maximum. So I'll just make my breaks run from 0 to 2600 to make sure I'm capturing both of those endpoints. And I'll have them break every 40 calories. So I'll define this variable called myBreaks, and then I'll pass that as an argument or an optional flag here to the histogram function. And you notice if we do that, we get much finer bin sizes here, and you're starting to pick up much finer scale features. So I'm not 100% sure what these little peaks are about. Maybe it has to do with the fact that a lot of people order a burrito, and burritos all tend to be about 800 calories. Maybe a lot of people order a burrito and guacamole, and so you get, another spike here of all the burrito and guacamole orders. Maybe these are all the salad orders. Not 100% sure, but there's obviously some regularity here, some kind of piling up at certain values that suggests patterns of popular orders, at least to me. Okay. The other thing that it suggests to me is that there's a lot of calories in most Chipotle meals. We can quantify that a little bit more specifically, so we might just compute a mean, and that's pretty straightforward to do. Ask for the mean of the calories variable inside the burritos data set right there. It looks to be 1,093 calories. Good Lord. We could also get the mean and other measures of central tendency here and dispersion using the favstats command. And if you recall, this favstats command is defined in the Mosaic library, and you had to have loaded that Mosaic library at the very beginning in order for that to work. Okay, so there you go. There's the mean, the standard deviation, the number of points in the sample, no missing data here, so a lot of useful information from that favstats command. All right, let's start looking at quantiles here. So one of the questions was, what percentage of meals at Chipotle have more than 1,600 calories, which is sort of the low end of the Food and Drug Administration's recommended daily allowance for adults, about 1,600, 2,400 calories. And the way we do that is using the pdata function, also defined in the Mosaic library. Okay, so for pdata, you feed it a quantile here, 1,600, and it'll tell you what probability or quantile level that corresponds to. Okay, so if we ask for p-data of calories at q equals 1,600, what we get is a number here. That number is 0.887. That's telling us that 88.7% of the calories in this distribution are to the left. And let's just kind of check the histogram to see if that makes sense. 1,600 is about right here. And sure enough, yeah, it looks like, about 88% are to the left, which means that roughly about 12% are to the right, and that's the number we want. So it's not actually this 88.7. What we want is 1 minus that number to get us the fraction that are to the right rather than to the left. So what is that number? Looks about 11.2%. Those are the ones that are greater than 1,600 calories, meaning that 88.7% are less than 1,600 calories. Okay, so that's getting a probability or a level from a quantile here. We can also go the other way around using the qdata function. And so this says if we want the 10th and the 90th percentiles of the burrito calorie distribution, we pass those as flags to the qdata function. And this would tell us that the 10th and 90th percentiles are 620 calories and 1,614 calories respectively. And so those two numbers there would form the endpoints of our 80% coverage interval. Okay, so there's our warm-up. Let's move on to the data set on Mercedes S-Class cars. And there are a lot of possibilities for exploring this data set. One of the things I asked you to do is to make it multivariate, so try to get 3 variables at once, one of which is price. And given the sheer variety of variables in this data set, it's very easy to tell interesting stories. And in fact, the hard part is to kind of narrow it down to one rather than tell a lot of stories at once. So the one that I chose to focus on here, one thing that was interesting to me initially was maybe look at region, right, and see if we plotted the price versus mileage. In other words, how much the drop off in price is as the car gets more miles on it, and to see if that was different by region. So that was my first thought here. Why that? Well, if you ever bought a used car, it's probably a good idea to buy a used car that was used in the South rather than used in the North of the United States. Cars in the North tend to, they have a lot of salt that gets churned up from when they salt the roads. They just have a lot more cold and weather damage associated with them. So, my thinking was that if I'm going to buy a used car, 20,000 miles on a used car means, a lot less, kind of damage to it if it's bought in, say, the Pacific or the South of the United States, than if it was bought in, like Chicago, the Midwest, or those, Minnesota winters or something, or maybe in New England. Now, I admit, that was my first thought, and it's kind of hard to tell from this plot right here if there's any kind of difference. Maybe you could say that the price drops off really, really steeply here for the New England cars and a little bit less steeply for these South cars, but it didn't jump out to me when I saw this picture. So, that was kind of, I wouldn't say swing and a miss, but I tried something that was kind of my initial thought, and the story wasn't immediately clear to me. Okay, so the next thing I looked at was plotting price versus mileage stratified by trim. Trim here is kind of the submodel of the car. Okay, and when I tried that, well, let's make sure. Yep, there it is. It's coming up here. When I tried that, this had to me like a much more interesting story here. So there's a lot of different trim levels here. This car appears the S-Class 63 AMG is really, really expensive. New cars are $250,000 or more. And you notice that there's an enormous drop-off in price as you get even to 10,000 miles. That's a huge depreciation for that model. And you compare that relative degree of depreciation for some of these other that's the super expensive one. Some of the merely expensive ones out here, like the 430 or the 420 or the 350 or something, there seems to be a much less aggressive drop-off in price for those early mileage. So to me, this was like a really interesting multivariate story where it seems that the class, the trim level here, is modulating the relationship between how mileage affects price. And that's obviously something we'll learn to quantify later, but the picture seems to tell the story and the relative steepness of that decline and, for example, that decline versus, say, that one and that one for some of these very expensive supercars up here. Okay. So there you go, kind of two attempts, one that sounded nice, at least to me initially, maybe didn't bear out so well in the picture, and then one that I tried second and seemed to give a much better story in the picture. Okay, so a lot of things you could do on that problem, but those were the two things that occurred to me first. Let's take a look at the Austin Food Critics data. So I've already imported this one over here. If we look at the first 6 or 7 lines of this data set, every row is a restaurant. In Austin, we're getting information on its neighborhood, its type of cuisine, and then 2 scores that are assigned by food critics. How good is the food, 0 to 10, and how good was the feel, the atmosphere, kind of the ambiance of the restaurant, 0 to 10 as well, and then the price, the average price of a meal, which includes, appetizers, main course, tips, dessert, drinks, tax, the whole package. Okay, so the first thing you were asked to do is to just figure out which were the most expensive restaurant neighborhoods on average, and we just compute the mean. This function right here will say take the price stratified by neighborhood and compute the mean price within each neighborhood. And if you see what gets spit out to the screen here, you just kind of pick out by eye here. There's few enough neighborhoods to say, well, it looks like probably Congress Avenue is the most expensive. Looks like maybe 2nd Street is the second most expensive. So those two, maybe I'm missing one here, but those two look like the two most expensive neighborhoods to me in raw dollars. Which makes a lot of sense, right? That's downtown. There's a lot of business travelers, a lot of folks at the Texas Capitol. So a lot of expense accounts in Congress Avenue and 2nd Street. Okay, so there we go. Those are the most expensive. How about the least expensive? Well, UT students, no surprise. The Drag is pretty inexpensive eating as far as that goes. And then there's Bolden Creek, which also looks to be a relatively inexpensive neighborhood. All right, so that was part A. Then another question was which of these two variables, feel score or food score, predicts price better? And a very simple way to measure that would have been correlation. So you could compute the correlation between price and feel score, which is about 22%, versus the correlation between price and food score. It's a lot higher, about 53%. So that's a very simple way to address that question right there. There are more subtle ways to address that question. They give you the same answer here, that food score predicts price more accurately than feel score does. Here would be another way you could do it. Let's fit a linear model for price versus food score. And I should be plotting something here, right? So let's just make sure that we plot our data first. That's always a good guideline. So plot to make sure that, a linear model looks pretty reasonable there for food score. So let's fit linear model. So price versus food score for one model, price versus field score for another model, and then we can compare the residuals from those two models. So it looks like the standard deviation of the residuals for the food score model is about 23, whereas the standard deviation for the residuals of the field score model is about 27. So that's giving you a notion that this first model has a lower average residual and therefore probably is a more accurate prediction. So 2 different ways to quantify the same effect. There seems to be a lot more information in the food for predicting the price than the feel. Okay, then the final thing to do was to take a mechanism for adjusting the price by the food score. In other words, to try to adjust for the systematic effects that exist between restaurants wherein the ones that make better food are going to tend to be more expensive. So a simple way to do that is to take the residuals from this first regression model up here, where we regress price on food score. So what's left over here? Well, our interpretation of the residual here is price adjusted for food score, the part of price that cannot be explained anymore by the quality of the food. So let's extract those residuals and store them in this variable called adjusted price. And now let's compute the mean adjusted price for a neighborhood. So before it was the mean actual price, but now we've adjusted price for food score. And the picture's a little bit different. So it still looks like Congress Avenue area has the highest price even once we adjust for the quality of food. But 2nd Street is no longer in second place. It's now the convention center, right? So probably the argument would here be that the 2nd Street restaurants are more expensive in raw dollars, but it's better value because the food is better in 2nd Street than it is over by the convention center, where there's probably even more travelers there than Congress or 2nd Street. As far as the best value restaurants, so it's probably Congress Avenue and Convention Center that look to be the worst value by this metric right here. In terms of best value, well, the drag shines, right? Decent meal at a decent price. Hyde Park also shines. Those look to be the two neighborhoods that have the largest negative residuals, which suggests that you pay a lot less than you would expect to systematically in those two neighborhoods than you would expect to pay on the basis of the food quality you're getting there. So there's all three problems. We can talk about those a little bit more in class if you want, but hope you have been able to learn something about comparing your answers to the walkthrough answers here.